When a chiral alkyl halide reacts with a powerful nucleophile such as hydroxide, an inversion process occurs. The nucleophile approaches the electrophilic carbon from the back, the opposite side from which the leaving group is breaking off from, and produces a stereochemically inverted substitution product. Valuable clues to the nature of this mechanism are as follows. First, rate experiments show the slow step to depend on the concentration of both nucleophile and electrophile. Second, the reaction only happens with primary and secondary alkyl substrates. Next, steric crowding around the electrophile lowers the reaction rate. Finally, when a chiral starting material is used, only the inverted product is isolated. The SN2 reaction is a bimolecular concerted mechanism with only one step. The nucleophile must approach the alkyl halide from the opposite direction from which the leaving group is breaking off. This is necessary for the nucleophile to deliver its electron pair into the sigma star antibond of the bond that is holding the carbon and leaving group together. The system will go through a transition state, as shown, in which the attached alkyl groups have flattened out into a trigonal bipyramidal arrangement. Negative charge is now developing on bromine and being lost from the hydroxide nucleophile. As the transition state collapses, the bromide is lost from one side of the molecule and the attached alkyl groups will relax in that direction to give the inverted product. The mechanism arrows are summarized here, with the nucleophile attacking the electrophile and the leaving group being displaced. Considering some examples from the chemical literature. When 2-naphthol is deprotonated with hydroxide, the subsequent alkoxide may be alkylated with an alkyl halide to produce the ether. While this is certainly an SN2 reaction, there is no observable inversion since the alkyl halide is primary. In the next example, the stereochemical inversion is observable from spectroscopic data. The acyl bromide on the carbohydrate cycle is replaced by azide, with the nucleophile ending up in the equatorial position, as would be expected from a stereospecific inversion process. For the third example, the sulfonate ester on the enantioppure stouting material is displaced by the nucleophile to give the inverted stereochemistry as part of a natural product synthesis. Overall, the SN2 reaction occurs with inversion of configuration at the electrophilic carbon. The nucleophile has to attack from the opposite direction from which the leaving group is breaking off, since that is where the open anti-bond is found. The pathway produces only the inverted product, and the SN2 reaction is therefore said to be a stereospecific process in which the stereochemistry of the product is dictated by the stereochemistry of the starting material.